Good afternoon, my name is Levi Hackman and I'll be presenting the project for Group 12. The project is a robotic arm with computer vision sorting. I will be covering three areas, that is, what the system does, why the market demands it, and the engineering problem it solves. My segment addresses the project description, our markability analysis, and the problem statement with its four objectives. I will first begin with the system itself. A box enters the workspace where an overhead camera reads the QR code on its surface and determines where that box belongs. A robotic arm on a 24-inch linear rail moves into position, lowering a suction effector and then confirming a vacuum seal before lifting. The arm then places the box at its assigned destination with no human involvement. Every lift, the system will also measure the weight from the motor current and store it for future reference. This is a fully autonomous, vision-guided sorting machine. But this leads to the next question. Why does the market want this? Monroe's motivated sequence makes the case. For attention, manual sorting consumes time, money, and labor. For need, small operation need automation, but industrial systems cost tens of thousands. For satisfaction, our system delivers autonomous sorting at a fraction of the cost. For visualization, near zero errors, lower expenses, and workers can be redirected to higher value tasks. And for action, investing in a modular platform that delivers from day one. That is the argument, but now let me show you the evidence. The U-Arm Swift company raised close to $1 million on Indiegogo against a $10,000 goal. The Rochix Dex arm raised $847,000 on Kickstarter from over 1,600 backers worldwide. Both use tiered campaigns with add-on modules, exactly our strategy. A base unit, a premium configuration, and optional upgrades. Two campaigns over $1 million combined. The demand is validated, and with that established, I will turn to the engineering problem. Manual box sorting is repetitive, error-prone, and does not scale. We have four objectives. 1. Read the QR code and resolve the destination from a configural mapping. 2. Pick with suction, confirm the seal, and place without dropping. 3. Operate autonomously and halt safely after repeated failures. 4. Estimate weight from actuator current and store it for reuse. To conclude my section, the system, a vision-guided robotic arm that sorts autonomously, the market, validated by over $1 million in crowdfunding, and the problem, 4 measurable objectives that govern the design. Now, I will hand it over to presenter 2.
Hello, my name is Mark Osborne, and in this segment, I will be going over the intended users and uses, and then going over the background, which will consist of the competing products that will validate our architecture and show where we improve upon. The intended users are going to be operators of small-scale sorting and storage operations who need boxes routed to their correct destinations without continuous manual handling. During operation, the user initializes the system and then supervises it from outside the arm's range of motion. They intervene only to hit the emergency stop or to perform a manual reset after the system halts on repeated failure. The intended use is straightforward: automated identification and placement. The camera locates the box, decodes its QR code. The arm picks it up with a suction. It confirms the vacuum seal, and then the box is placed in its destination. If the system cannot complete the pickup after multiple attempts, it is halted and then it signals an error. This failsafe is built into the design and is not bolted on as an afterthought. We reviewed 3 competing products. The first is the High Wonder Max arm, an ESP32 based open source desktop arm with a suction nozzle and WonderCam AI. It performs sorting through inverse kinematics and even includes mounting holes for a sliding rail. While the MaxArm relies on one-click color sorting, we use QR-based identification with a configurable destination mapping, which is far more precise and flexible. We confirm a vacuum seal before every lift. The MaxArm does not. And we perform self-calibrating weight estimations based off the actuator current, a feature the MaxArm does not have. The second product is the Dobot Magician, a 4-axis arm with great repeatability, a 500-gram payload, and a suction cup. The Dobot offers conveyor belt and sliding rail accessories. It is a proven platform for the current class of sorting that we are targeting. Our project improves on it in 3 different ways. First, our system is purpose-built for sorting with QR-based routing, not a general-purpose desktop arm that just so happens to sort. Second, our integrated linear rail extends the workspace without sacrificing payload capacity. And then third, our autonomous fail-safe operation and weight learning features are not standard on the Magician. We also reviewed a third product, the NeuroNet 2. To review, I covered the intended users, small-scale sorting operators, and intended use, autonomous QR-based identification and placement with failsafe handling. I then showed how our system improves on the Highwander Max Arm and the Dobot Magician through QR-based routing, seal confirmation, and weight learning. And I covered the NeuroNet 2 as a third reference.
Hello, my name is Alex Sisson and I will be the presenter for the intellectual property portion of this presentation. I will be going over the two most relevant patents concerning our project as well as how we will avoid infringing upon those patents. The first patent is the robotic suction grippers. This covers a combination of a suction gripper, a vacuum source, an imaging device, and control logic that coordinates motion and airflow to move an object based on imaging data. Our project will require all of these components, but we will differentiate in our implementation and design. We're going to use QR-based identification as well as configurable destination mapping, implementing a novel feature of a self-calibrating weight estimation from the actuator current, and we will also be using a simple vacuum pressure sensor to confirm the seal as opposed to the airflow control mechanism outlined in the patent. The next patent is the identifying and processing of objects. Now, this patent covers the identifying of objects through machine-readable code, as well as using a robotic arm to move said objects to their assigned locations. While our project uses QR reading as well as routing boxes to their assigned locations, our application will be far narrower in scope. We will also be using fixed identifier to destination mapping for a known set of boxes in a flat workspace environment, and we will not be identifying arbitrary items in a heterogeneous string. We reviewed one final patent, the object grasp system, but we will easily avoid infringing this one by using one single overhead camera as well as the vacuum feedback as opposed to the force and torque sensors and dual cameras that the patent outlines. In summary, through our use of QR code mapping, a single camera configuration, vacuum pressure confirmation, and current-based weight estimation, we will be allowed to achieve our project goals without infringing upon any of the patented combinations we reviewed. Next, I'll hand it over to the presenter for ethical considerations.
Hello, my name is Virgilio Chudio, and I am presenter number 4. I will be presenting on the ethical considerations and the social impact of our senior design project. So for ethical dilemma, we pose ourselves a question of how do we balance the economic benefits of automation against potential labor displacement. So we had 4 options when we went to answer this question. Option number 1 was halt development. We gave this a low score as it didn't really solve anything. Option number 2, which is automate without mitigation, we gave this a low score as well, as it does solve things, but it completely disregards ethics. Option number 3, automate and reframe the labor. We gave this the highest score, and we chose this option. The reason we chose this option is because it was the meeting point of the engineering and the ethics. People would keep their jobs, and the engineering would still do the job it was meant to do. And option number 4, limit to assistive use. We gave this a medium score because it directly protects the jobs, but it limits the engineering. The good life. So what does this design say about us? When we went to answer this question, we basically went about it in 3 different bullet points: human value, meaningful work, and responsibility. For human value, we wanted to prioritize the human's time and safety over tedious, repetitive work where humans can lose focus and make mistakes. Meaningful work frees people to focus on creative and high-value problem solutions instead of repetitive work that is just boring and soul-crushing. And responsibility. We design our product to support the workers, not to replace them. We design and present the system to support a beneficial outcome for the people it affects. Overall, in review, we have strongly considered most of the options that we could see with our senior design project. We have found that by allowing workers to go to an observational role where they simply verify that the product is doing what it's meant to do, we will protect both the ethics and the engineering side of things. Thank you.
Hello. In this final section, I will discuss our concept selection,
present the final system architecture, and conclude with our proposed solution for autonomous box sorting. Our team evaluated two concepts. The fixed base arm was simpler and less expensive, but it could not reliably cover the entire workspace without sacrificing stability. The rail-mounted arm expanded the workspace through linear motion while maintaining payload capacity, stability, and full camera coverage. As a result, the rail-mounted configuration was selected as our final design. This diagram shows the architecture of our selected system. A fixed overhead camera captures images of each box. Image processing software decodes the QR code, determines the box location, and identifies its assigned destination through a configurable mapping. The microcontroller then plans and controls movement of both the linear rail and the 4 degree of freedom robotic arm. A vacuum sensor confirms a secure seal before lifting, while current sensing estimates the box weight for future reference. Together, these components enable autonomous identification, handling, and sorting of systems. In conclusion, our system combines computer vision, QR-based identification, vacuum suction handling, and weight estimation into a single autonomous sorting platform. The rail-mounted design provides the best balance of workspace, coverage, stability, and payload performance. To review, we selected the rail-mounted arm as the best concept, developed an integrated system architecture, and designed a reliable solution for automated box sorting. Thank you for your time. We are Team 12.